Hello everyone, today we're going to be talking more about collisions. For elastic collisions, we have momentum is conserved, P initial is equal to P final. We have kinetic energy is conserved, K initial equals K final. These two conservation laws, conservation of momentum, conservation of energy, both lead to these two other equations that we see here. This third one tells us that the relative speed between our two objects is fixed. This third one can give us what the final velocity of one of the cars is given the two initial velocities and the relationship of their mass. So let's watch a video and see if we can work out how fast the purple car is moving after this collision. Alright, so in this collision we had the red car moving down the ramp. When it gets to here, V red initial is 2 meters per second. So let's go and write down a few of the things that we know. One is that the mass of the red car is 83 grams and the mass of the purple car is 50 grams. We also know that the V initial for the red car is 2 meters per second, and we know that the initial velocity for the purple car is 0. So we can go and we can use these first two relationships up here and be able to solve for the two final velocities of the cars that we want to know. So we want to find out what is V red final and what is V purple final. This is kind of what we want to know. Another thing that we could use is these two equations down here, which are going to make our life a little bit easier. So we're going to go with those. So this one tells us that the relative speeds are fixed. So here we have V, so B's here are going to be, is going to be this purple car. So V purple initial minus V red initial is going to be minus V purple final minus V red final. So this tells me that the purple initial, that's 0, so this is going to be minus 2, it's going to be equal to, I'm going to carry this minus sign, and I'm going to get V red final minus V purple final. So the difference in the velocities after the collision should give me 2 meters per second. Alright, so what I'm going to do is use this equation to tell me how fast the red car is moving. And so that's going to give me M red minus M purple all over M red plus M purple times its initial velocity, that's just the 2, plus VB initial, that's 0, so I don't even have to bother with this term. So I can go ahead and plug in a few of the things that I know. And so I'm going to get V red initial is going to be my 83 minus 50 all over this 83 plus 50. And then all of that is going to be times 2. Now you can wonder why I didn't go in and convert these masses into kilograms, and that's because this is a ratio, and because if I convert the top both into kilograms and the bottom both into kilograms, when I'm dividing by 1,000, I'm dividing by 1,000 in the bottom, and that'll just cancel it out. So I don't need to bother with that. So when I plug this in, what I'm going to get is about 0.5. And so when I plug this in, what I'm going to get is about 0.5 meters per second. Now I can work out what the purple car final is going to be, and I can use this relationship here. So the purple car needs to go away at 2 meters per second because the relative velocities have to remain fixed. So initially this guy was moving 2 meters per second toward this guy, so after the collision that guy better moving 2 meters per second away from the red guy. So here's my two velocities. So in this problem we looked at our two masses. M red we said was the 83 grams, M purple is our 50 grams, and we found our initial velocity for the red car, that was that 2 meters per second. V purple initial is our 0, V red final is 0.5 meters per second, and V purple final is 2.5 meters per second. Now what we want to check here is energy actually conserved? So Ki is going to be 1/2 M red V red initial squared. So we go ahead and plug in what we know. We're going to get 0.16 joules. Now we do the same thing for K final, but here we have to have both cars included in this measurement because they're both moving. And when we plug in what we know here, we're going to get our 0.16 joules again. So these two are equal to each other. We know, yes, this is an elastic collision. So now I'd like to go back and talk a little bit more in detail about this equation. So this equation is a consequence, again, of our conservation of momentum and conservation of kinetic energy. So this equation right here, we're going to consider the limits of this. What I mean by that is, what happens when MA is much bigger than MB? So in this case, MA, the car that's moving along or whatever, here we have car A, and let's just say it's going to collide into B. So A is very massive, and then it's going to collide into B, which is not so massive. So VA is going to be, well, when we plug this in, we get big number, MA, which is a really big number. We can imagine like 10,000 minus 1 over 10,000 plus 1 times VA initial. And then since we said B was at rest, we don't have to worry with that term. And so here we're going to get big number over big number, but these are both pretty much the same number, so this is just going to give me a 1. So that tells me that VA final is pretty much going to be VA initial. So a real world example of this is car plus bug. When the car collides with a bug, your velocity doesn't change. But let's see what happens to the bug if the bug was elastic. So VB final, when we look at this, this tells us that the relative speeds are before the collision and after the collision is fixed. So since the car was moving at V towards B, and then after the collision we have A still moving at V, so that means that B needs to be moving at 2V. So that means B went from 0 to 2V in this elastic collision. So let's consider one more case. Here we're going to consider what happens if MB is much bigger than MA. So A is moving along and it runs into a stationary B. But in this case, B is the one that's really massive. So when we look at VA final, we're going to plug in maybe a really big number for B and a really small number for A. And so you can see that this is going to give you 1 over 1. And so then what we expect is that VA final is going to be minus VA initial. So one common case of this would be this video right here. Where the car comes running in and hits a wall. And if the collision is elastic, the car will just bounce off the wall. Or another example is a ball bouncing against a wall. Since the wall is so massive, the ball just bounces away with the same speed that it bounced into the wall. So let's consider one final case where A is moving and B is moving towards A, and they both have a speed V. So this time we can't just toss this term out. So let's consider if A is much bigger than B. So here VA final is going to be equal to, in this case we have A really big, so this fraction right here is just going to be VA initial. We have 1 minus a tiny number, 1 plus a tiny number, so it's just going to be what we have. And then in this case we're going to have 2 over MA plus MB, but in this case A is really big, so this is our really big number. So this is going to be 0. So again, VA is totally unaffected by what's happening by B. But what happens to VB final again? And in this case, their relative velocities is remain fixed. And so what we end up with is that VB final is going to be equal to VA final plus the difference here, which is going to be another 2V. So it's going to be end up with 3AF. So it's after the collision, we have A still moving this way with speed, with velocity V. But after the collision, B has to turn around and go 3 times faster back the other way. So B's change in velocity is actually 4V. So problem 5.68, we have you and a friend are playing with a medicine ball. This is just a ball used at gyms that is fairly massive. You can imagine maybe 10 kilograms, that's a bit much, but it's a massive ball, much bigger than a basketball, much heavier than a basketball. But you and your friend have gotten a little unfriendly, and you'd like to knock your friend down. To achieve this, you suggest to your friend he should catch the ball or he should let it bounce back elastically. So here we have 2 different conditions we have to consider. One is catch. So if he's going to catch the ball, if we draw a picture, you throw the ball at your friend, right? And now sometime later, your friend catches the ball. So initially, the momentum was M medicine ball, V medicine ball. Your friend doesn't have any momentum. After the collision, you have mass of your friend plus mass of the medicine ball times their velocity that they're going to go. So momentum is conserved. In this case, since it's being caught, this is not an elastic collision, so we can only talk about how momentum is conserved. So this is going to tell us MB VB equal to M friend plus M ball times this V final that we want to find. So here V final is just going to be V of the ball, and then now I'll ratio these 2 masses, MB over M final plus MB. In this case, the ball is moving this way. Your friend is standing still. And now sometime later, you want the ball to bounce back elastically with whatever velocity that is, v final. And now your friend, in order to conserve momentum, is going to go this way. So that's v friend final. So v b final is going to be equal to so VB final BV final is going to be equal to the difference in the masses. We get that from that fourth equation that we saw. The ball minus the mass of the friend all over m ball plus m friend, and then v initial. So we could go ahead and estimate kind of what this is going to be. The ball is about 10, maybe your friend is 50 kilograms, maybe 70 kilograms. So the difference in this is going to be minus 40 over this 60. So this is minus 2/3 v. What has to be true if this is an elastic collision is that the relative velocities here is fixed. So that means that your friend moves, since this is v, it's going to be 1/3 this way. So we can compare that with if they caught it, and here you're going to get mb, which is just the 10 over the 60, so here it's 1/6 v. So you can see if your friend bounces it off of them, their recoil velocity is much bigger than if they just caught the ball. So if you want to be unfriendly, tell your friend to just try to bounce the ball back to you, and that has a better chance of knocking them down. Alright, so here we have some expert who wants to measure the velocity of a bullet. The bullet has some mass. It's going to collide inelastically with a block of wood, and we got the mass for that guy. After the collision, the bullet is embedded, so that again is inelastic, in the wood, and the two move together at a speed here. So let's go ahead and draw this out. So here we have the bullet moving along with some initial speed. We have the block of wood hopelessly sitting over here. Sometime later, we have that bullet and the block of wood both moving at a speed of v equals 3 meters per second. So this is a simple inelastic collision, so all we have to do is consider conservation of energy, of momentum. So our initial momentum is just the bullet times v bullet. And our final momentum is going to be mass of the bullet plus mass of the wood times v of them together. So we should solve for this VB, because that's what we want to find, is what's the speed of the bullet before it collides. So here we're going to have v of them together. And then now it's this ratio of their masses. MB plus MW divided by MB. And so we plug some numbers in. We get this 3 meters per second. And then now 3 for the block of wood plus 0.02 for the bullet divided by 0.02. And when we plug this in, we get about 450 meters per second. Our final problem is you trying to show off your physics knowledge to your little cousin. You grab a basketball and a tennis ball. you tell your cousin that if you just drop the tennis ball, you can make it bounce higher than it started just by dropping it, which seems pretty unreasonable. If you just took the tennis ball and you dropped it, the best it can do, because of conservation of energy, is go back to its initial height. We know that if you drop a real tennis ball in the real world, it bounces like this and eventually gets smaller and smaller. So what you're claiming here is actually pretty interesting. So just by dropping that tennis ball, it's going to bounce up really high. And the way that you do this is you drop the two of them together, the tennis ball and the basketball, like shown, with the tennis ball on top and the basketball on bottom. And you drop them together at the same time from a height of 1 meter. How high up will this tennis ball fly? So that's a lot of information, and where to start is first to write out what we know. So we know all the masses. Mass of the basketball is 0.6 kilograms. Mass of the tennis ball is 0.06, so there's an extra 0 there, kilograms. And if we are to find out what's going to happen, you can kind of visualize the picture. Let's start here. So you drop the two and they start to fall down. So initially their speed, since you're dropping them, is 0. And then just before they reach the ground, they're going to have some speed. That we're going to want to find out. So after you drop them, there's going to be a collision here. So there's going to be the two collide here. And then after the collision, this tennis ball, at least according to this problem, is going to fly up high into the air. And so this is kind of this delta x, the height. And that's what we want to find out. So we want to find this height. So in order to do this, we're going to have to kind of work backwards. To get this height, we could go to our kinematic equations. One of them that kind of stands out is this one. V final squared is V initial squared plus 2a delta x. That's really nice because there's no times in here. We just have this x. We want to find that x. We have velocities. We can probably get that from what's happening in this collision. We can think about conservation momentum, energy there. And we know A, that's just gravity. So if we know the velocity of the tennis ball after this collision, we could use this and get to this height that we really want to get to. So what we're going to have to first is find out how fast are these balls going as we drop them down. So actually we're going to end up using this guy again to solve that. So if we had a tennis ball and you drop it 1 meter, how fast is it going down at the bottom? Alright, so that's just V final squared is going to be V initial squared plus 2a delta x. So let's put x positive going up. We know that acceleration is going down. That's gravity. We know that our initial is 0, and that final is what we want to find out. So V final squared is going to be equal to 2 minus 9.81. Delta x is x final, which is 0 minus 1, so that's a minus 1. So then V final is going to be the square root of 2 times 9.8, and that's going to give us our 4.4 meters per second. Now since you dropped them both from the same height, they're both going to fall 1 meter. So both the tennis ball and the basketball are reaching the bottom at this 4.4 meters per second. But since we dropped them with a tiny little separation here, the basketball hits the ground first, collides with the ground, we assume that this collision is elastic. Otherwise we couldn't solve the problem. So as it bounces down, it's going to bounce up with exactly the same speed. The direction of its velocity is going to change. It was going down and now it's going up. And so the tennis ball is going down and the basketball is going up. Sorry, basketball. This one's tennis ball. And so now we have a collision, and that's this right here, this step. So one thing that we know is that we can use the relative velocities. We could just use conservation of momentum. That makes it pretty simple. Or we could use that fourth equation that we saw on the other slide. I'm just going to use conservation of momentum because it's easy enough here to work it out. So MB VB initial plus MTVT initial. That's going to be our initial momentum. And so we could just plug in what we know. That's the 0.6. VB, the ball is moving up, so that's that 4.4, plus mass of the tennis ball, 0.06, times it's moving down, so that's a minus 4.4. So when we plug that in, we get our 2.37 kilogram meters per second. That's our initial momentum. And this is going to be equal to the final momentum. And that's just mass of the basketball v basketball final plus mass of the tennis ball v tennis ball final. It has to be equal to this 2.37. Another thing that we know is this relative speeds are fixed. So initially, the relative speed is VB initial minus VT initial, and that's just going to be 4.4 minus a negative 4.4, and that gives us 8.8 meters per second is their relative velocity. So that has to be equal to VT final minus VB final. So here I almost have something like what I do up here, and I have it equal to just a number here. So I have two equations, two unknowns. So here's kind of two equations, two unknowns. So what I'd like to do is to get rid of something. So here I have a minus sign, here I have a plus sign. So if I multiply this whole thing by MB, and I'll do that here, MB VT final minus MB VB final is going to be equal to MB times this. And what I can see is that this equation, this modified 2, if I add it to this guy, this term is going to drop out. And so what I'm going to end up with is this MT VT final plus MB VT final is going to be equal to 2.37 plus MB times that 8.8. So now I just have this equation, and I can write out it all in terms of this VT final. MT plus MB is going to be equal to this 2.37 plus MB 8.8, and I'm just going to solve for this VT. So 2.37 plus 0.6 times 8.8 all over 0.6 plus 0.06. So when I do this, my VT final is going to be 11.6 meters per second. So that's all just getting me to this point. So now the tennis ball is moving up at this 12 meters per second. So now how high does it end up? I just end up using this equation. So it starts here at 12.6. At the very top, the V final is 0. V initial is this 12.6 meters per second. And gravity is going down. So V final squared equals V initial squared plus 2a delta x. So V final squared, don't have to worry about that. That's going to be 0. So now I'm going to have V initial squared equals minus 2a delta x. So then delta x is going to be equal to V initial squared all over minus 2a. So here I'm going to have that 11.6. Got to square it. Minus 2 times a minus 9.8. When I plug all this in, I'm going to get 6.8 meters. So just dropping the tennis ball on top of the basketball, the two fall down. They reach a speed of 4.4 meters per second. After the basketball collides with the ground, it bounces back up, hits the tennis ball. The tennis ball shoots up at 12 meters per second and will eventually reach a height of almost 7 meters.